Okay, so welcome back. Right now we're going to do a few example problems. We'll do one in this video and one in another video. They're kind of long, so we broke them up into two videos. But the first one, this one right here, is a classic example of a non-calculator critical point and extreme value problem that you could face on the AP exam. So do yourself a favor. When you're working on this problem on your own, don't pull out your calculator. Don't pull out Desmos. See if you can solve all this stuff without a calculator. Okay, so we got the following function, x cubed minus 2x squared plus x plus 1, and we have a definite bound for that function, so it has some endpoints. So what you guys should do right now is just find all the critical points. All right, pause the video and give it a shot. All right, so if you want to find the critical points, remember the critical points are that f prime of x is equal to 0 or equal to undefined. So let's find our first derivative right now. So the first derivative of this is going to be 3x squared minus 4x plus 1. So you might be saying to yourself, well, how in the world am I going to do this without a calculator? Well, remember some of those skills we talked about you would need to know at the beginning of the year. One of them was factoring, okay? You can always apply the quadratic formula to this, but we could also factor this. So why don't you actually give it a shot, try to factor it yourself without my help, pause the video. So if you get it, you should have gotten this factored into this. So this would have given us two solutions to that is equal to 0, which would have been x is 1/3 and x is equal to 1. Okay, so remember, factoring, very quick and easy way to find zeros of a particular function. So we got our critical points now. Is there a place where f prime of x is undefined? No, this is a function that's continuous everywhere, so we're all good. We don't have to worry about it being undefined. All right, so let's go to the next part of the question, which is now that we have our critical points, find the minimums and maximums of the function. Okay, recall that we had f prime of x was equal to 3x squared minus 4x plus 1. So see if you can figure out where all the minimum and maximum points of this function are just given that derivative. All right, so if you gave this a shot, one way that I like to do these problems is draw something called a number line, where we have x values right here. And what we do is we put in all of the values of our endpoints or our critical points in here. So the endpoint is -1 and 3. And in between there, we have critical points of 1/3 and 1. All right? So then what we want to do is we want to evaluate what our derivative is at these points. Well, we found on the previous slide that the derivative is 0 at 1/3 and 1. Let's figure out what it is at the endpoints, okay? We plug in a value at this particular endpoint, -1. If we plug that into this equation right here, we will end up getting, let's see, that'll be 3 plus 4. So we're going to get a positive number. So we get a positive value right here. 3, we will once again get a positive value. All right? So remember what we said, for example, about endpoints, okay? In this case, -1 is a left endpoint. When our derivative is positive in a left endpoint, we have a minimum. When our derivative is positive in a right endpoint, we have a maximum. So there we go. We got two mins and maxes right there by just looking at the endpoints, okay? Now, since we know that the derivative hits 0 at 1/3 and 1, we know that it's going to be positive all the way from -1 to 1/3, because if it was going to switch to negative, there would have to be a place where it crossed 0 or at least was undefined. All right. Likewise, we know the derivative is also going to be positive between 1 and 3. So now let's just find what the derivative is going to be between 1/3 and 1. Okay. Good value to plug in right there is maybe a half. Okay. If you plug in something like a half, it doesn't really matter what you plug in. If you plug in any number between 1/3 and 1, you should get that the derivative is negative. So now that when we have a derivative go positive, 0, negative, that's a maximum. And when the derivative goes -0, positive, that's a minimum. So there we go. We solved all of them right there. Okay. Now, we could have found the maximums and minimums at the what I call the interior points or the critical points another way. We could have also looked at the second derivative. So our second derivative will be 6x minus 4. This is equal to 0 at x equals 2/3. Okay, so we can add 2/3 to our number line right here. And then if we go down and we add a little area for the second derivative, we know that will be 0 at x is equal to 2/3. So let's plug in a number less than 2/3, okay? When you're on the non-calculator sections and you're doing these number lines, or even if you're trying to evaluate functions at certain numbers a little bit less than or a little bit greater than other numbers, you should always be thinking of 4 numbers to plug in if you can plug them in. Those are negative infinity, 0, 1, and positive infinity, because when you plug those 4 numbers into any equation, they're going to be the easiest ones to determine what the value of that equation is. And in this case, we don't need to know what the value of f double prime of x is. We just need to know, is it positive or is it negative? So with our function f double prime x, remember that was 6x minus 4. Let's just plug in x equals 0. 0 is to the left of 2/3. So when we get that, we get a negative second derivative. If we plug in a value greater than 2/3, let's say 1, we will get a positive second derivative, okay? Remember what we said about derivatives. If the first derivative is equal to 0 and the second derivative is negative, meaning that it is concave down, that once again means we have a maximum. Likewise, the second derivative test says that if the first derivative is 0 and the second derivative is positive or it's concave up, we have a minimum. So basically we had 2 ways of confirming for these critical points what the minimum or maximum were, and we could have used that second derivative test. So again, just 2 ways to do the same thing. All right, so let's go here to Desmos and see how we did. So there's our function right here. We saw that at the left endpoint was indeed a minimum because the first derivative was positive there. Then we had our derivative go positive to 0 to negative. That means we had a maximum right here at x equals 1/3. That's 1/3. It looks about right. At x equals 1, our derivative went negative, 0, then positive. That means we had a minimum. That looks like a minimum to me. And if we zoom all the way out, let me clear this ink right here. I've never seen that before. So let's just erase it normally. Okay? So also, if we look at our right endpoint, our derivative was positive to our right endpoint, meaning we had a maximum. So we were right everywhere. So again, without a calculator, without any kind of graphing whatsoever, we just use calculus to figure out the exact locations of minimums, maximums of our particular function. So in the next video, we're going to look at a case where we actually need to utilize graphing software or calculators to figure out locations of extreme values.